Calculating steady-state sinusoidal system responses is relatively easy. In fact, it's so easy that it's one main reason we like to assume that all of our systems are linear. However, it only seems easy if you're proficient with complex arithmetic. This video briefly covers complex numbers and complex arithmetic. Imaginary numbers are based on taking the square root of -1, which is indicated by either an I or a J. Physicists, most engineers, and mathematicians usually use I. In electrical engineering, I is reserved to indicate electrical current, so electrical engineers use J to indicate the square root of -1. Since this is a circuits class, I'll use J. Since squaring any number results in a positive value, no real number satisfies this equation, and this number has no meaning in the real world. Keep in mind that J is just a number, not some kind of variable. Let's take a look at some examples of what I mean by this. First, let's look at the square root of -4. This can be written as the square root of 4 times the square root of -1. Since the square root of 4 is 2, this is just 2 times J. Any imaginary number can be written as a real number, for example 2 times J. Next, let's rewrite J squared. Substituting the square root of -1 for J means that this is equal to the square root of -1 squared, which is just -1. Finally, I'll simplify the inverse of J. I can multiply this by 1 in the form of J over J, which results in J over J squared. Since from the previous step we saw that J squared is -1, this is just equal to -J. Complex numbers contain both real and imaginary numbers. For example, 5 minus the square root of -4 is the sum of a real number and an imaginary number. It's 5 minus J times 2. These two terms can't be combined because they're completely different types of things. Since real and imaginary numbers don't share anything in common, they're independent of one another, and they can be used to define an orthogonal coordinate system. Graphically, the real part of the number is displayed on the horizontal axis, and the imaginary component is on the vertical axis. This set of axes is often referred to as the complex plane. Any complex number can be represented as a point on the plane. If I have a complex number a that equals little a plus j times little b, I can plot that point as shown here. When I write a complex number in this form, it's in rectangular coordinates. I'm given the distances in the x and y directions on my axes. The real part of the number, little a, is the distance on the horizontal axis. The imaginary part, little b, is the distance on the vertical axis. If we have a complex number, capital A, that's equal to little a plus j times little b, it corresponds to a point in the complex plane in rectangular coordinates. The distance along the real axis, little a, is called the real part of the complex number. Mathematically, I'll write that as RE of a. The distance along the imaginary axis, little b, is called the imaginary part of the complex number, capital A. It's denoted as IM of a. Notice that little b is the distance on the vertical axis and does not include the j. J times b is imaginary, but b itself is a real number. The j just tells us which axis b is on. Next, I'll talk about representing complex numbers in polar coordinates. As usual, the point is represented as a magnitude, which provides the distance the point is from the origin, and a direction in the form of an angle from the positive x-axis. For complex numbers, an alternate way to express the number in polar coordinates is this. The magnitude is now multiplied by a term of the form e to the j times theta. E to the j theta is called a complex exponential. It still provides the direction information, but in this form there's actually a multiplication process involved. In the original form, we're just presenting two pieces of information, a distance and a direction. Some arithmetic operations, such as addition and subtraction, are easier to do in rectangular coordinates, while other operations, like multiplication and division, are usually easier in polar coordinates. This means that conversion between coordinate systems can make the complex arithmetic much easier. First, I'll talk about conversion from rectangular to polar coordinates. A complex number in rectangular coordinates is in this form. It provides distances in the real and imaginary directions. The same number in polar form looks like this. It gives a magnitude and a phase angle from the positive x-axis. The magnitude in polar form is the square root of the squares of the real and imaginary parts according to the Pythagorean theorem. Notice that the imaginary part b does not include a j. The angle is the arctangent of the imaginary part divided by the real part. Again, don't include a j here. In trigonometric relations, you need to check the quadrant on the inverse tangent functions. Now let's do a couple of examples of conversion from rectangular to polar coordinates. My first example is a is equal to -2 minus j times 4. So the real part of this number is -2 and the imaginary part is -4. To calculate a magnitude, I take the square root of the real part squared plus the imaginary part squared. -4 squared is 16, -2 squared is 4, so this becomes the square root of 20. Theta is the arctan of the imaginary part, -4 over the real part, -2, which from my calculator gives me 63.4 degrees. Now I have to check to make sure I'm in the right quadrant with this number. 63.4 degrees puts me up here in the first quadrant. The real and imaginary parts are both negative, however, so I need to be in the third quadrant. I can get to the correct quadrant by either adding or subtracting 180 degrees from this number. If I add 180 degrees, I get 243.4 degrees in this direction, or -116.6 degrees in the negative direction. I can choose either of these numbers. They're both the same angle. I'm going to choose -116.6 degrees. So, in polar form, a is the magnitude, square root of 20, at an angle of -116.6 degrees. In complex exponential form, it's the square root of 20, the same magnitude, e to the j times the angle, which is -116.6 degrees. Now let's convert the same complex number from polar to rectangular form. The real part, little a, is the projection of this number onto the real axis. Since the real axis is adjacent to the angle theta, that means that little a is equal to the magnitude of a times the cosine of theta. Little b is opposite to the angle theta, so little b is the magnitude of a times the sine of theta. Keep in mind that little b is a real number that gives the magnitude of the imaginary part of the complex number. Now let's do a couple of examples of conversion from polar to rectangular form. If I have a number, a, which has a magnitude of 2 at an angle of 45 degrees from the real axis, to convert to rectangular form, the real part is 2, the magnitude, times the cosine of 45 degrees, and the imaginary part, which multiplies j, is 2 times the sine of 45 degrees. The cosine of 45 degrees is 1 over the square root of 2. The sine of 45 degrees is also 1 over root 2, so my number becomes 2 over root 2 as the real part, plus j times the imaginary part, which is also 2 over root 2. Next, I'll talk about arithmetic using complex numbers. I use different coordinate systems to perform different operations, since the choice of coordinate system can simplify the mathematics. This means that the conversions between polar and rectangular coordinates that I talked about earlier are indispensable. First, I'll talk about the conjugate of a complex number. The complex conjugate of a number simply changes the sign on the imaginary part of the number. The complex conjugate is indicated by a star superscript. An arbitrary complex number can be expressed as a is equal to little a plus j times little b, which is shown graphically here. The complex conjugate of a is just little a minus j times little b. Graphically, changing the sign on the imaginary part just flips the complex point around the real axis. In polar coordinates, Since the complex conjugate reflects the point around the real axis, the sign on the angle of the complex number changes. So the complex conjugate of the magnitude of a at an angle of theta is simply the magnitude of a at an angle of the negative of theta. Addition and subtraction of complex numbers is most easily done in rectangular coordinates. If the numbers are provided in polar coordinates, my first step before adding them will be to convert them to rectangular coordinates. So I'm only going to talk about adding numbers after they're already in rectangular coordinates. Our two complex numbers are capital A and capital B. Capital A is little a plus j times little b, and capital B is little c plus j times little d. To add complex numbers, add the real and imaginary parts individually. The real part of the sum is the sum of the real parts of the two original numbers, a plus c, and the imaginary part of the sum is the sum of the imaginary parts of the operands, b plus d. Subtraction is performed similarly. Just take the difference between the real and imaginary components of the two original complex numbers. Addition and subtraction is easiest in rectangular coordinates. Whatever you do, don't try to add the magnitudes and the angles of a complex number in polar coordinates to sum the numbers. That doesn't work. Now let's do an example of the addition of two complex numbers. I'm given two complex numbers in polar form. I want the sum of those numbers in polar coordinates. To do the addition, I need to convert these to rectangular coordinates. So the real part of this is 3 cosine of 45 degrees, and the imaginary part is the magnitude 3 times the sine of 45 degrees. Cosine 45 is 1 over square root of 2, so this is 3 over root 2. And sine of 45 is also 1 over root 2, so this is j times 3 over root 2. Converting this to rectangular form, this is 5 cosine of 135 degrees plus j 5 sine of 135 degrees. This is negative 5 over root 2. And this is j times 5 over root 2. Now to do the sum, a plus b, I add the real parts. So this becomes 3 over root 2 minus 5 over root 2 plus j times the sum of the imaginary parts. 3 over root 2 plus 5 over root 2. This is negative 2 over root 2. Plus j times 3 and 5 is 8. Now I've got the sum in rectangular coordinates. Now let's convert that back to polar coordinates. So a plus b, the magnitude is the square root of the sum of the squares of the real parts and the imaginary parts. So this is the square root of negative 2 over root 2 squared plus 8 over root 2 squared. The angle is the inverse tangent of the imaginary part over the real part. So this is arctan of 8 over root 2 over negative 2 over root 2. This turns out to be the square root of 34. And this is approximately 104 degrees. There's our answer. Now let's multiply our two complex numbers a and b. First, I'll do this in rectangular coordinates, and then I'll use polar coordinates. In rectangular coordinates, we have to take the products between all of these cross terms. So we multiply little a times c plus jd and j times b times c plus jd. J squared is negative 1, and the final result is this. The real part is AC minus B times D, and the imaginary part is BC plus A times D. Now let's multiply in polar coordinates. In polar coordinates, our numbers are in this form. Multiplying them is the product of these two terms. Remember that E is just a number, and that the product of a number raised to two different powers is simply that number raised to the sum of the powers. The product of these numbers is then equal to the product of the magnitudes times e raised to the sum of the angles. When multiplying two complex numbers in polar form, just multiply the magnitudes and add the angles. This is usually less prone to silly mistakes than the four products and two additions you have to perform in rectangular coordinates. So I usually prefer to multiply complex numbers in polar coordinates. Now let's do an example of multiplying two complex numbers. In this particular example, I want the answer in both rectangular and polar coordinates. I'm given the numbers in polar coordinates, and multiplying in polar coordinates is easier anyway, so the first thing I'm going to do is get the result in polar coordinates. So a times b is equal to 3 at an angle of 45 degrees times 5 at an angle of 135 degrees. I multiply the magnitudes, 3 times 5 is 15, and add the phases, 45 and 135 is 180 degrees. That's my solution in polar coordinates. Now I'm going to take this one and convert that to rectangular coordinates. So a times b in rectangular coordinates is the magnitude, 15, times the cosine of the angle, which is 180 degrees, plus j times the magnitude, which is 15, times the sine of 180 degrees. Cosine of 180 degrees is -1, so this is minus 15, plus the sine of 180 degrees is 0, so this is j times 0, so this is just -15 in rectangular coordinates. Now let's talk about division of complex numbers. I'll start out with the same two general complex numbers. So a divided by b is this. The problem is that I can't divide by a complex number. The trick here is to multiply by 1 in the form of the complex conjugate of the denominator divided by itself. If I multiply out the terms in the denominator of this expression, I get c squared plus d squared. The numerator has 4 terms. 2 are real and 2 are imaginary. If I group the terms, I get this. Now each of these terms is just a number, and I'm done. Next, I want to do the same problem in polar form, which, for me at least, is less susceptible to simple mistakes. Here are the two complex numbers in polar form. Dividing a by b gives this. I'll leave the ratio of the magnitudes in this form, but I'll move the angle of b into the numerator by changing the sign on phi. As when I was multiplying complex numbers in polar form, I can now add the phase angles and group these e terms. So this expression turns into the ratio of the magnitudes times e to the j theta minus phi. So to divide a by b, I divide the magnitude of the numerator by the magnitude of the denominator to get the magnitude of the result. The angle of the result is the angle of the numerator minus the angle of the denominator. Now let's do an example of division of two complex numbers. These are my two numbers. I can divide those directly in rectangular form. In that case, a over b would be 2 plus j3 over 4 minus j. Now I would need to multiply top and bottom by the complex conjugate of 4 minus j. So that would be 4 plus j over 4 plus j, which is going to be 2 plus j3 times 4 plus j over 4 squared is 16, and j times negative j is 1. Now that's going to get arithmetically kind of painful. So let's take a look at doing this in polar form. First, I need to convert the two numbers to polar form. The magnitude of a is the square root of 2 squared plus 3 squared, and the angle of a is the arctangent of 3, the imaginary part, over 2, which is the real part. This is the square root of 13 at an angle of about 56.3 degrees. B is the square root of 4 squared plus -1 squared at an angle of the arctangent of the imaginary part, which is -1 over 4. This is square root of 17 at an angle of about negative 14 degrees. Now to divide these two, A over B is equal to this. The magnitudes are square root of 13 over square root of 17. To get the magnitude, we take the ratio of these two magnitudes. And the angle is the angle of the numerator, 56.3 degrees, minus the angle of the denominator, so minus negative 14 degrees. This is square root of 13 over 17, and its angle is 70.3 degrees. Finally, I'll quickly summarize a general strategy for performing complex arithmetic. The emphasis here is on which coordinate system to use to make the arithmetic easiest. Addition and subtraction are definitely easiest in rectangular coordinates. You just add or subtract the real and imaginary parts of the operands to get the real and imaginary parts of the result. If your operands are in polar form, it's invariably easier to convert them to rectangular form before trying to add or subtract them. Multiplication and division are usually easier to do with complex numbers in polar form. For multiplication, multiply the magnitudes of the operands to get the magnitude of the result, and add the angles of the operand to get the angle of the result. If you're dividing, divide the magnitude of the numerator by the magnitude of the denominator to get the magnitude of the result. Then subtract the angle of the denominator from the angle of the numerator to get the angle of the result. Now that we've got some background on complex exponentials and complex arithmetic, let's revisit sinusoidal steady-state circuit analysis and use these tools to determine circuit responses.